Okay, let's talk about discovering our senses. So now we're trying to, we learn about the cord, we learn about the brain. Now we're going to talk about receptors. How are we going to get things into the system from the outside world? Well, from the inside body as well, but also from the outside. Sensation is a word we use for creating awareness around the change in the internal and external environment. Internal and external environment. Whew. That means I all of a sudden see something. That's a change. That's a sensation. And a perception is its conscious interpretation. What does this mean to me? That's what the perception is. So that's actually the Buddhists take that a step further. They call it the one arrow, two arrow of pain. The first arrow of pain is the sensation, oh, I twisted my ankle. The second is the perception, oh, I'm such an idiot. Or, oh, I just twisted my ankle. And so they call that, like, we humans create pain for us, or something's just happened, but we usually make it worse and create extra pain because we're beating extra hard on ourselves, what an idiot we are, or that is so stupid, or whatever is going on with that. So that's the two definitions, sensation, perception. Sensation requires the brain involvement. Sensation requires the primary cortex involvement, and then perception usually requires the further association sort of cortices working with it. That's all receptors like. So the result of when we have a change in the outside world, that change is being transduced from a change like a pinch into a nervous energy by a receptor. And so we got multiple receptors. We got some receptors that are superficially. Those are like these, they're like in the skin. These are like pain receptors, they're just nerve endings. You cut them, it hurts. That is pain. Or we got other ones, they're like onion layered ones looking things. Those are kind of cool. They have like layers around them. And when you push deep pressure, those layers start touching each other, and then that fires a nerve off. So it's like, that's kind of a cool system. So that's sort of a type of receptor that we have in the skin. Also the mucous membranes are there. Then we have deep receptors. Those are muscles and tendons and joints. So that's like proprioceptive receptors and proprioception, telling the body where we are in space. That's usually in the muscle and the joints and tendon. And then we have visceral receptors, internal organ receptors. And then of course we have what we talk most about in this class, which are the special senses. So we're looking at vision mainly, but we also there have hearing, balance, taste, and olfaction, which is smell. Those are our special senses that we talk about. Receptors can be classified by stimulus type. What do they transduce? Do they transduce mechanical deformation, like a pressure or a change like that? Do they transduce temperature, like heat, cold, chemicals? Photo is pictures, and nociception is pain. Nociception is pain. Or we can also classify them by structural complexity. And so that's when then the complex receptors become the special senses, and the simple receptors are the ones that just transduce general sensations either through free or what we call encapsulated nerve endings. And the free nerve endings are the ones like the pain that I showed you in the other slide, that just are nerves sticking up their fingers, and when we cut them, that hurts. And then they send a signal up. Or we have these encapsulated ones that that onion layer type is one of those nerve endings. Yeah, right here. This is the one that we can see the onion layers, right? Or the layers of cell membrane. Many of the receptors that we have adapt when they're continuously stimulated. So continuous stimulation reduces the sensitivity of that stimulus. So for example, you Yeah, look us. We go right back to the monkey. But when you stick a hand in a cold water, in a cool water, and you stick a hand in a hot water, the other one, and then you go with both hands into the lukewarm water, the one from the hot will feel cold, the one from the cold will feel hot. That's adaptation. They get used to it. Adaptation means get used to it. And that means get used to the stimulus. So that's a good thing to kind of know. That's why when you start the shower, it's cooler, well, many times. And then you leave it at the temperature, you go out the last time you go back in, you burn yourself. Proprioceptors proprio means one's own. So what they do is they monitor movement, body movements via stretch receptors. So that's what they do. Proprioceptors, yeah, they're important. If we don't have them, we don't have a clue where we are in space. So the proprioceptors are, for example, responsible for us to be able to close our eyes and still hit the nose with a finger. You're not looking. How can you know where that thing is going? That's a question it just works. That's proprioception. That's also a very interesting concept, like when well, let me go forward here first. Nociception, nociceptors are the other ones that basically then they do not adapt. That's the end result of those. So those two do not adapt. We don't want them to adapt. Noci means danger. And so danger is a threat that tissues get damaged. For us though, as an experience, that's pain, even though it means danger. So when somebody has a really, 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 really bad pain, the back is classics, like they think they're dying. And it's really, really bad pain. The tissue is stretched, squeezed, pulled around, and is very acute, so they have to pay attention to it. So they cannot just ignore it, and then they damage the tissue. If you twist your ankle, you gotta hurt, otherwise you're gonna keep twisting that ankle. So if those would adapt, if we would get used to that stimulus of pain, and the body just integrates it, and you would walk on a twisted ankle, you would destroy the tissues very, very fast. And so that's important. That's an important reason why they do not want to be adaptable. And then the proprioceptors also don't, because you always need to know where you are in space.
How does pain tolerance play into that?
That's more of a brain question.
Oh.
Mm-hmm. Because, well, actually maybe not only. I mean, for example, if you expose your tissue, like that example of the lady who just drank coffee and has fibro and things like, why the heck I should not have fibro? It's like, you got to start drinking some water. And so that is a chemical question. And dehydration is a huge, huge problem we have for tissue health, because we don't drink. I should drink this in a day as a gallon with my activity level. I get about 3/4 of it, and then I'm like, I'm done with it. But it's trying. So that can help with that pain, and a lot of the pain adaptation, or the getting used to it of the pain, or it gets worse over time, right? That is uphill, because if the post-central gyrus is where we get these sensations come in first. So you hurt in here, and you just continuously hurt in here. That part of the brain gets always stimulated, and at some point it's like it gets smudged. It's not as clear defined anymore what's what. And so all of a sudden it's not just here, it's also here, even though the stimulus is only here. But the brain doesn't understand anymore. And so we have to backtrack. So one of the things is work with the tissue. That helps a lot with redefining the homunculus. And then also movement. That also helps a lot with that. But it's tough. It's a tough one. Or were you asking the people who just, they have, they doesn't bother them? Those people?
Also the higher tolerance, if that's what I was wondering. People that
Yeah, and I think that has a lot to do with how your brain's set. Or a lot of times, you get women and they have given birth to babies. That tolerance completely changes of what their level of acceptance is.
Yeah.
That's when you go get the guys we're always babies, unless they're high athletes or so. They just got to take it. Where these two play nicely together is actually it's called the gate theory in medicine, and it was established in the mid-50s somewhere. And it's the fact that when you create pain, like you hit your thumb with a hammer, the pain signal travels to the brain via the spinal cord. But when you then put proprioception on top of that, like you rub the thumb, those pain fibers cannot travel together with the proprioceptive fibers through the brain, through the spinal cord into the brain, and the gate closes for the pain to go to the brain. So they call it the gate theory for some reason, because the gate closes. And that's basically when the kid, you know do it with the kids all the time. The kid runs into the wall and hits a forehead and go like, "It's okay, baby." And you kiss it and you rub it, and this is exactly that concept. I talked to a guy who does spinal cord stimulus, whatever, machines in the spinal cord. Not anything you ever want to have done. And same concept. With people with really chronic pain, they put that sort of a stimulation thing in the spinal cord, electrical, and they have like all these different patterns and things that they can shoot the nerves up, and then that closes that gate. But it's the same concept ultimately. And so that's why when you do studies on, they have one orthopod, he did studies on baseball, football, hockey. An injury that knocks a baseball player out, they play ball, they run, they sit down. Not that much movement if you think of continuous motion. They get on the bank, they can't play anymore. A football player will play through such an injury. But they have commercial breaks, so they got to stop and wait. Then a hockey player, they just move all the time. So they are working through a lot more injuries than the other profession. Not that that's good. That's just an indication of the more we move, the less we feel that pain. You know, I don't know how they are when they're 50. That's a different discussion. So that's a very good that's like, I talked to other professors about that. I didn't learn it in anatomy school. That was later, but I think it's very important. The others, they didn't know what I was talking about. And so the gate theory is very interesting to understand a lot of chronic pain. And then this is also kind of cool, that many receptors are responsible to monitor specific surface areas, a specific area of the skin. So some of those areas are going to be very big. So there's one nerve just going to a big area here of the skin, and some do very small areas. And so we call that a receptive field. And so we can figure out how large a receptive field is, like basically meaning how large the part of the skin is where one nerve goes to. Hello. And we can do that with a 2-point discrimination test. So we can take 2 needles and poke people and say, do you feel 2 points or 1 point? And like in the thumb, you feel 2 points really close to each other. So that's a small receptive field. That gives us a high resolution. So you can put your hand, put your hand in a pocket and you go and feel like, oh, that's a dime, that's a nickel, and so that's a very small receptive field. Then you go to the back. And the back is like, I don't need to feel coins with the back. So we don't need to worry that much about it. So we can make a very large receptive field in the back. So I can massage here I want to massage, close together, it's much narrower. And in the back, I can spread my fingers apart. The patient doesn't necessarily feel the spaces in between. They think, whoa, you got big hands, like frog hands. That's the receptive field question. So that's kind of cool. And that brings us to the eye. So the eye and vision. The organ of seeing includes the eyeball and the optic nerve and accessory organs such as the eyelid, eyelashes, lacrimal apparatus, and eye muscles. Oh, I like those. The lacrimal apparatus is the tears. That's the tear gland. The eyeball itself lines in we see the bony orbit right in here in every skull. We see that. So they are in there. They're embedded in some fatty tissues in there, so they don't get banged against the bone too heavily. When we look at the eyeball itself, we have some layers from the outside to the inside. The first layer is of whites. The white layer in the back, we see the eye white. That's the sclera. That's the whites. And then that's the clear. The cornea in the front is when it gets clear. Oh, you can see through it. So those two together make an outer shell of the eyeball, and that's called, as a collective, we call it the fibrous tunic. Tunic meaning layer. No, coat. I think tunic means coat. Lots of collagen fibers in there. Always, when you think of the outside shell of something, lots of collagen fibers. They resist stretch. They maintain the eyeball's shape. So that's all till about here, the white stuff. And then in the front, we still have a lot of the toughness, but now it's clear. And then that's the cornea, the clear. Then underneath that, we have what's called the vascular tunic, and that has two functions. It limits light reflections, and it gives us blood vessels that supply the eyeball with blood, which is very important. Blood you always associate with food and oxygen, and getting rid of, waste. So those are two things in the we have vessels, and then in the back we have the limiting light reflection. So, I don't know what happened to those eyeballs. They didn't make the eyeballs. Well, we'll have to see about that. But in the back, when you open an eyeball, you see there's some darkness. You can see when you open those eyeballs there. Let's open those eyeballs. Well, actually, we can see the reflection in the other ones. Here we see the vascular tunic as the blood vessels. We see these. Also, what also goes to that vascular tunic is the ciliary muscle. And the ciliary muscle is in the front. That's right here, right here. Right where before, right here, this up here, before it gets curved. And this muscle has ligaments attached to it. We call them suspensory ligaments, and they contract, muscles contract, they contract and they let go, and that makes the lens get flatter or more round. And that helps us accommodate for different pictures, for different distances. So that's a very important function there. See, this is a pretty nice picture here, how you can see these ligaments, these suspensory ligaments, they call them, and then they go into the muscle, and if the muscle contracts, it bulges up, and if it flattens, it stretches out. And so that length difference pulls on those suspensory ligaments and makes the lens flat or more bulging. And then we got an iris, and that's still the vascular tunic. And the iris is basically the color of the eye. What's your color of the eye? And that's two muscles, one that's a circular and one that's one's a sphincter and one's a dilator muscle. So the parasympathetic nerves go into this round muscle that closes the eyeball down and makes the pupil. The black thing here is the pupil that we see through. It's basically a hole that light goes in, and the sphincter muscle constricts that pupil, makes it very small. And then when we have sympathetic stimulation, when the line's in the corner, you got to run away from it, and you got that thing needs to be open, so we get as much light in and as much information into the brain. We're going to have these dilator muscles pulling on it and opening up that eyeball as wide as possible. And so then we have a large pupil. So that's when the black is really dark. You see it in a cat really nice. You get the cat from a dark to a light space, and then it really shrinks together. So that's what the iris does. So that's the color of the eye. And then we have the internal tunic, and then we have the retina in the back. And the retina are these cells, there's a tissue, and then there are these cells here, and these cells are the photoreceptor cells. And so these cells are actually changing light into electrical impulses. That's what they do back here. These are rods and the cones. We're going to talk about that a little more. And then we also have some pigments that we don't have. We don't have too much spattering light going around. So one of the things we got to be careful in the eyeball. We get all that light coming in, and if the light reflects onto a surface, we don't want it to bounce off and then bounce all over the eyeball and give us a goofy picture. We need a lot of the light be absorbed by pigmented epithelium and then in the back where the light goes on to, that's where the cell then can directly pick up that light. Ooh, that's a lot of picture. And the inside of the eyeball, so now we cut through these layers there. Now we're on the inside. We have a back portion and a front portion. The back, this is where the sclera is. So this back here is all the whites of the eye. And in there we have what's known as a vitreous humor. And the vitreous humor is mostly water, but it's also a lot of hyaluronic acids. It's a gel. It's like a bubbly gel thing. When you cut it, you can see it doesn't just leak out like water. It's like very, very light jello. And that stabilizes the eyeball. So that kind of pushes from the inside out on the eyeball, and then the sclera is all that collagen fiber that holds it tight. And so it's not, you know, we went to the cadaver and it's dehydrated, the fluid goes out, so the eyeball doesn't have its firmness then. So that's what that does. And then in the front, we have the aqueous humor. So that, what we have here is we have the lens. The lens makes a boundary here. And then in the front, we got this aqueous humor. And the aqueous humor is one that gets continuously exchanged and provides nutrients. The back here, this one is there and it stays there. It does not get remade and newly made and all that stuff. In the front, we actually get it constantly made, and it gets secreted. You see here, it gets made and then it gets secreted out in what they call the canal schlemm. And so if we have an ocular pressure problem, we're looking at the front aqueous, the aqueous humor, because most likely these things here are clogged and the liquid cannot flow back out. Oh, here, that's that one. Glaucoma. See, glaucoma is a rise in intraocular pressure. You heard of glaucoma before? I know, you get that sometimes. And it can be leads to the damage of the retina. If this pressure gets too big, it can push too hard, and that can damage the retina. We do not want to do that. Oh, look, and that gets me to the stuff that moves the eyeball around, so we can actually see in different directions. And so those are the external extraocular muscles. Uh-huh. The who? Glaucoma is an increased pressure in the eyeball. Oh, yellow? That's jaundice.
Is it cataract?
Is it floated in the cataract where they can't see through?
You know how like some people are born with like brown eyes and then they get older, the eye turns red?
Or have like the white, right?
Yeah.
Like much older?
Like a lot of older people? You'll
Like
see
a
that
much
their-
older?
Their eyes are like white.
Yeah, oh.
Right.
Yeah, I'm not sure if that's a glaucoma. No, I see it, but I'm not sure if that's an indication of glaucoma.
I don't know if it's glaucoma or cataract. I don't know.
Yeah, I don't know. I think it might be
But it's
cataract. I
like
think it's more, it would be more
cloudy.
cataract than
It's like
glaucoma.
cloudy color.
Yeah, because the cloudy color is the lens. That's the glaucoma. I mean, it's the cataract. Yeah. We'll have a slide on that. So when we look at the movement of the eyeball, we're looking at 6 muscles that move the eyeball around. So you got these red things on the eyeball. Those are the 6 muscles. So you see your eyeball. So you got one on top, one on the side, one on the bottom, one on the inside. Outside, inside, actually. And you see this. You see this? That's your lacrimal gland. That's your tear gland. That's where the tears come from. That always sits on the outside. You didn't, when your mom tell you when you cry, when you have something in the eye and the tears come out? No, I know you never cry, but in case you would, you grow up this way and not this way? No?
No.
God, I'm the only one. I always the only one. Maybe I was dreaming that, I don't know. But that's because the tears get made here on the outside, they move to the inside, and by the nose they drop down. That's why when you cry a lot, you need tissue. Because you gotta go somewhere. You don't want to eat them. And so that's why my mom said you do this and not this, to get the sand corn out of the eyeball. But anyway, this is always on the outside of the eyeball. So this is always out here. So that is always lateral. So then we have 4 muscles that are parallel laid down. So we got one on top, we call that the superior. And that muscle is a straight muscle, goes straight back, it's parallel. So we call that the rectus. Rectus means straight. So that on top is the superior rectus muscle. Then we got one on the bottom. You can see it right down here. That's the inferior rectus muscle. Superior, inferior. We learned that first lesson, superior, inferior. Then we got one on the outside, by the gland. We call that the lateral rectus. And then we got one on the inside, away from the gland. We call that the medial rectus. Good test questions. It's all the same word. Then we go to the mess it up. 2 more. So now with these, actually, let me say this. With these, we can look up, we can look down. So if this contracts, what do? You look up. It pulls on it. It's attached down back here by the bone in a tendon, and it pulls on it. So the superior rectus will pull it up. Inferior rectus will pull it down. Lateral rectus will pull the eyeball outward, and medial will pull it towards the nose. Those are the functions of those muscles, right here. But then we gotta have these motions that go diagonal a little bit. And so we got 2 more muscles. We got a superior oblique, and we got an inferior oblique. And the superior oblique is right here. It's attached back here too, where everybody else is attached. And then it goes down here, and it has a pulley, like a thing that sticks the ligament, a band that it goes through, and it takes a sharp turn, and it anchors into the bone right here. I mean into the eyeball, not in the bone, the eyeball. And so that's really strange. So this muscle, on this eyeball, this is the medial side. The muscle comes from back here, travels towards the nose, and has a loop it goes through, and then it anchors into the eyeball right here. That's a superior oblique muscle, superior oblique. And when you look at what it does, you just gotta kind of go with what I'm saying. It moves the eyeball down and out. So it goes like that, down and out when it pulls. So the superior oblique moves the eyeball down and out. So you're looking down there, that's your superior oblique. That way. Now with the whole head. And then the superior oblique. And then the inferior oblique is a little simpler to see. It's right here on the side. You can see on the outside, you see it goes right into here. And so it comes from underneath and it wraps right here into the outside. And that one, when we contract it, moves it, the eyeball somehow, the way it moves it up and out. Up and out. So I have a hard time visualizing that all the time. So I just know they both go out, and the superior oblique moves it down, which is the opposite, which is the paradoxical thing, right? And the inferior oblique moves it up and out. And then I memorize that. Then I'm good with that. But that makes some very good test questions. You better study those. Mm-hmm.
What about like down and in?
Down and in. We can look there. That's a combination of the medial rectus and the inferior rectus. I know I asked that question too, because why the heck do we have muscles that go out and not in? I haven't gone there yet. When I have a call with the chief upstairs, I'll tell you. But we call it evolution. How about that? That sounds good. Good. So that moves the eyeball around. We talked about the different layers a little bit. Now we can go to the retina in the back, and those are the light-sensitive photoreceptors in there. And the retina is a series of 3 levels of neurons. I'm not showing them here, but I'm showing them here. You see, here's a level, number 1. Then here's a level, number 2. And then these are the 3rd, and then they go together and make this optic nerve that comes out of the eyeball. In the back, that's the hole for the nerve to come out, back here. But that's crazy. Think about it. That's crazy. The light has to go in here, go through all these cells, to then transform into electricity back in here. And then the electricity travels back out there and out the eyeball. And that's probably one of the reasons why our vision is, you know, considering animal worlds, probably mediocre or less than that. But that's okay, we don't want to see everything. So the cool thing is when let's go back here. So we have these 3 levels of neurons, and then inside the first layer, we have the ones that transduce the light. We have rods and we have cones. We have 2 different types. And so they are laid back there in the back of the wall. And inside them, inside those rods and cones, we literally have light absorbing retinol molecules. They change shape from a straight to a cis when activated, and that transforms into an electrical impulse, and ultimately that gives us the light that we see in the brain. And so basically it's very complicated, but what I learned from this is it goes down to a molecular level that the light can shift the molecule, and then that fires off the nerve. And it gets us to see because of that. And then once they are stimulated here, these are those rods and those cones, they then go to the bipolar cells, they call those. That's that type of cell that has an axon and a dendrite coming out of its body, one on each side. That's one of those types of cells that we studied under the nerves. And from there, they relay to the ganglion cells, and then they exit the optic nerve, and that goes then to the brain. And on the brain, where is my brain? On the brain, you see down in here these 2 stumps coming out, right by the pituitary gland. Those are optic nerves. So the eyeball is right down in here, and then the nerve comes out and goes right, and then becomes that. Or that's it, it's just cut off right here. So that's then the optic nerve. We have 2 different types of these cells that absorb light. Ones are called the rods, and they are light and dark sensitive, and they are actioning, they're happening when we pick up dim light. Those we mostly see black and white. When you go outside and it's dark, you don't see as much color. You see a little greenish, but most is black and white. And then the cones are responding into vision, to color vision. So those pick up really the bright lights that we see when it's light. What's interesting is when we go into a dark, in the light we always activate the cones. So when it's light, the cones are active. The rods are overpowered. Because when it's not enough light, when it's dark, the rods are very sensitive. They pick up a little bit of light, and then you can see in the dark. That's why when you go from the inside, from here, from light to dark, you first can't see nothing, because we have to first get, now let's go back. When we're in light, when you go from dark into light, it's bright, right? It's like, oh, it's so bright. That's because the rods get all this light coming at them all at once, and they get what they call bleached out. They got overpowered. That's why sometimes it almost hurts. When it hurts like that, it's your rods hurt, because they get overpowered. I mean, they are used up, and that overpowering happens after a moment, after a minute or so. Then you pick up all the light from the cones, and the rods don't even work no more. They're sort of too much for them. And then you go from the light to the dark, and it takes about 20 minutes to accustom to the darkness, because we gotta unbleach all of these first and get all that light out of them, and then they can pick up electricity. Then they can pick up light again and make electricity again, and that's when you have real good dark vision. And that takes about 20 minutes. And so that's where you can see the difference between the rods and the cones in our everyday life. And the optic disc is a place right here in the back that has most concentration of, the optic disc, sorry, that's not the, no, that is the optic disc right here. That's where the nerve goes in and out. The optic disc, you can see where all the blood vessels, these are all blood vessels, they come together, they go in and out of there. And that's where the nerve goes in and out. And this is an area we don't have any nerve picking up any light or anything in that area because there's no receptors right there. What we have though then, we have an area that's right here, that's known as the macula luteae, and it has a little fovea centralis, they call it, a little center in it, and that's an area where we pretty much only have cones. That's the center of the vision. So if we focus something in the center of the vision, that's what we see the best right there. And that light goes right in there. And so in that area, when you look at it, this is a cross section, you look at these cells here, 1 cell, 2 cell, 3 cells down in this area, in the fovea centralis, they're all pushed to the side. So all those extra layers, these are all pushed to the side, so the light goes straight onto the cones, and we have really good vision right there. So that's what happens there. That's the fovea centralis, the macula luteae. Good. Now, how the heck do we do that? So when we get light coming in, we have to figure out how to see with the lights coming in. So we have to project the image onto the retina, and what we have to do is smaller, obviously, the small eyeball is pretty small. We also get to be inverted of what we see because the light coming in has to be refracted, so it has to change direction when it penetrates into the eyeball. So when we penetrate, light goes into a curved surface, it changes the angle a little bit. You can see that in the glass. When you have a spoon in, the water changes the angle, and you have the spoon looks kind of weird that way, because that's that refraction. Light, I mean, red air refracts different than water. And so it has to, the light has to penetrate the cornea first, and then the lens, and then those are two curves that the light will do, two bendings, and then from there it projects onto the retina, and on the retina we need to have it in one little point converging that we have sharp vision. If it doesn't converge on the retina like that, we got a problem. We do not have sharp vision, we have blurry vision. And that happens when we have a short globe, for example. So actually the visions, the correction visions that we need to have is because the globe is too short or too long. And so if we have a globe that's too short, the pictures converge behind the globe, and we call that far-sighted, behind the retina, making close objects appear blurry. So what we need to do is we need to correct this with a lens that bends this light even more so it projects further forward. So we give it a more curved lens to then have the bending even here as well, not just here a little bit and then in the lens a little bit. So that way then, well, whatever lens we give them, that way then the image projects right onto the retina, not too far back. The opposite is the case when the eyeball is too long and the thing doesn't reach the retina. Then we need to give them lenses that curve the light less. It almost bends it the other way, because we need to reach further back and to reaching the retina. That's nearsightedness. So we need a concave lens for that. So there is a little bit of optometry. A lens also becomes thick and loses flexibility as we get older, and that requires then reading glasses. And that is in addition to the congenital malformations of the eyeball. That's because this is not as flexible anymore. I mean, the lens itself in here. That's why that is. And then that's about cataracts. So cataracts or when the lens, which is transparent, processes a lot of the sugars, the glucose. It has some metabolism, leaves a little bit of residue in the back behind it, and that clumping of protein causes these cataracts, these cloudinesses. Cataracts means waterfall, and we see cloudier than without cataracts. But these days they're pretty good at exchanging those lenses, I hear. So they fix that. So that helps. Astigmatism is caused by an irregular curvature of a cornea, and then the image is projected as a line rather than as a point onto the retina. And so that's sort of a picture of how people that have astigmatism could be picking it up. So it's like this curve is not smooth and uniformly curved. See here, it points forward a little bit more. That's an astigma. So it's like not the whole angle is all the same angle. And so you got a little problem with the projection of that. So that's interesting to know. I didn't know that for a long time. When we want to see how well we can see, visual acuity, we want to see if we can have two distinct points separated by 1.5 millimeter at 20 feet. That's the measuring. So 1.5 millimeter, that's like nothing by 20 feet. And so that gives us that visual acuity, and that's the Snellen chart that is made, and that's just sort of a standard of how to do that. And you've done that before, I'm sure. I'm afraid, I'm sure I'm going to do it again soon. You should do it on me. Can you see still? No. Not when you got your eyes closed. And then, okay, so now we've seen, we picked up light, we made some electricity out of that light, we have an optic nerve, and now where the heck does that optic nerve go? Well, right here, it comes out of here. So the visual pathway that is. So this is a little complicated. The reason why this is a little more complicated than just one way into the brain is because we see not just 2D, we see 3D. Have you ever noticed that? When you have an iPad, John, and you try to don't drive, it's really hard to see distance. When you walk, you probably walk into things, and we don't have that 3D component. And so with the eyes, we have this great thing where we have two pictures picked up just a little bit separated from one another, and that gives us this ability to see further into depth because we can overlay those two pictures in the brain. That's kind of like, have you seen these old things that have two photos and you look through them and then you see a three-dimensional thing? It's the same kind of concept. The pictures are a little bit apart from one another, and so it overlays that. And we can do that with our eyeballs because we have two. So let's explain it. So we have two visual fields. So this is what the eyeballs pick up. Visual fields are what they pick up. So we explain it that way. The right one and the left one. So each eyeball will pick up the right visual field and the left visual field. On this right eyeball, the right visual field is picked up by the medial part of the retina. On the opposite eye, the left eye, the right visual field is picked up by the lateral part of the retina. And then what we can do now is we can go and we can bring these nerves back and we can converge them and then deliver them to the same place in the occiput. And then we have two pictures from the same thing, a little bit apart from one another. And that gives us a three-dimensional image. And we can see. So that's basically what we have to do. And so the way we do it in the body, does that make sense? How both eyeballs pick up the same picture? Does that make sense? Like, look, you see, and a little bit of the seeing goes to this part, and it picks up this part of the retina picks it up more or less, because it looks this way. On the other side, it could not be picked up by this. That's on this side. So the light goes in and projects more to the outside of this eyeball. And so from having that ability for having the same picture be seen by two different eyeballs that are a little bit apart from one another, we can then go to the occipital lobe in the brain and overlap those two pictures, and they're a little bit separated. So that gives us that three-dimensional vision. Just that little angle. The brain can, compute that mathematically like a computer could do that. And so when I look at the brain itself, I have, let's take the green because that's what we did. So I have this visual field here. The right visual field is picked up by the outside part of this eyeball, by the inside, the medial part of this eyeball. As I project the optic nerve back, I get to this place right above the pituitary gland that's called the optic chiasm. That's the term, optic chiasm. And the nerve fibers that come from the inside part, the medial side, they cross over there. The other ones stay on the same side. And then back here, now we have nerve fibers from two different eyeballs get projected backwards. We call that area then not the optic nerve anymore. At that point, it's considered an optic tract. But I don't have you to memorize all these nerves. I just need you, I go through them so you know what they mean. And then this here, then they project, of course, where do they go? Thalamus. They always go to the thalamus. Everything always goes to the thalamus except for smell. And then from the thalamus, it goes to the occipital lobe, and that's where we have the primary visual cortex. And so that's where we then see 3-dimension. I think that's pretty cool. But we might have to talk about it a little bit before we really understand it. So that's what I write here. This way the left visual field of both the eyes get, or the right visual field, doesn't matter, get projected onto the same occipital lobe, here the right one, or vice versa, projecting each half of the original picture onto the opposite occipital lobe. Overlapping the image from both eyes helps us then see depth perception, which is 3-dimensional. One of the things that's cool about the eyeball is like it's inside that head thing, or the vision, it's deep inside the head. So if I have something going wrong, I can't just cut it open and look what's wrong. Go away, brain. No, that will not work. So I can understand the lesions along the visual pathway because they give us specific visual impairments depending on where along the pathway or the injury is. So for example, if you have a, well here, an optic nerve injury can lead to full blindness, obviously in one eye. But also a pituitary tumor inhibits the transmission of both the, temporal fields. We could take a lateral. They use all, in neurology, they use all these weird terms that they don't get rid of. Temporal means the temple, that's outside, that's lateral. That's what they refer to them. But they both, the outside parts of the visual fields get cut off, and we get something called the tunnel vision. So it's like we just see the tunnel, the inside, you don't see any periphery. And when a doctor sees that, and they measure that, it's like, can you see, how far can you see? They can sort of ideally get an idea. Maybe you have a pituitary tumor or something, because it squeezes these nerve fibers that cross over, and they can't cross over no more. And so we have this ability to sort of project, or diagnose inward, or at least then say, oh, let's take an MRI and see what's going on, because this is not so good. I mean, these days, at least we got MRIs.
We're studying.
Oh, you studied that picture? Oh, good. Did I make a mistake?
No.
Oh, good. Sometimes these get a little. Sometimes these can get a little confusing, if you don't do it all the time. All right, but that brings me to accessory structures. We have eyebrows, we have eyelids. Eyebrows are short, coarse hairs that overlie the skull's supraorbital margins. We studied that. That's right here. If you pluck them all out, then they do not help shading the eyes from sunlight. That's why you need a cap. Or the thing that really sucks when you work out, and it's all the sweat goes into the eyeball. That's also, it helps keep the sweat above the eyeball a little bit. So if they are no longer there, you need one of those bands or something like that. I know, we don't think of that when we think of the beauty. Eyelids cover the eye anteriorly. We have an upper and a lower eyelid. So when we close the eyes, that's what the eyelid does. It closes the eyes. It is strengthened by a connective tissue plate called a tarsal plate. So it's not as flexible as just regular skin. It has a little bit of strength to it. And it has a lot of sebaceous glands in it that grease the margins right where the eyelashes grow. So wherever you have a hair growing out of the body, you're going to have a sebaceous gland. On the inside of the eyelid, we have a little membrane called the conjunctiva. It's transparent, and it folds back. So it goes over the eyeball, and then, no, that's a tarsal plate. It goes over the eyeball, and on top it folds back, and then it goes the anterior side of the inside of the eyelid, on the top and also on the bottom. When we get that inflamed, we get pink eye. Anybody know pink eye? If you got kids, you know pink eye. Otherwise, we got to question the kids. The one thing with that is this is when you walk out with your kid and they got pink eye and it's like, go home. That's when they tell you to go home. Because this is very contagious. It's not dangerous or anything, you just don't want to be out in public so everybody has it. And the lacrimal gland, we talk about that. It's on the outside, lateral above the eyeball. Produce the tears. Tears are very mucus-containing antibodies, lysozymes. They clean, they nourish the cornea. That's nice to have. It's not just when we're upset. They drain from the gland through several ducts into the upper lateral part of the eyeball, and then from there they cross medially. They go across here. Oh, look, that's stuck in there. I have to take this out. Is that also in the booklet? Uh-oh, I didn't see it. I know, isn't that nice? I tried to underline everything. It took a lot of work. But anyway, from there they go medially, so they cross the eyeball over this way. And here we got a bunch of nice ducts, the lacrimal canals and the sac. Here's the canals, and then here's a baggie, a little sac. And then we drain them into the nose. That's why we need a tissue. Tissue. Okay, tonight. All right, you guys, you have to stick it out a little bit longer. You gotta be prompt of this is cool. We can do this pretty fast, but this is cool stuff. Hearing and equilibrium. When we think of the ear, we describe sensory organs that function for hearing and also for equilibrium, not just hearing. And they both work fairly similarly the way that they transduce the vibration or the position. Anatomically speaking, the inner ear is where the petrous portion is located in the temporal bone. So when you open the skull, that's right here, that little mountain. And when you see this, that's that thing. That's like a large part of the skull right here. And so out inside there, we got these bone carved out things in the bone. And so we got to study those carved out things a little bit in the bone. We have an external ear and a middle ear, and they both conduct the sound wave. So we have an external ear right here, and then we have a middle ear right here, and then we got an inner ear right here. So the external middle ear conduct the sound waves. The former consists of a funnel-shaped auricle. That's where you hold up the kids. No, don't. Not anymore. In the 70s, maybe. And that's elastic cartilage, so it will go back to the original shape if you twist it around. And then that's followed by the canal, the ear canal. We also call that the external auditory canal, or meatus. Remember that from the skull? And we're ending in what we call the eardrum. And that's just a little small round thing like a regular drum that you can play on. So that's called the eardrum. Tympanic membrane. I know, when you look at we have a real skull, you see it, it looks like a small tiny djembe. You know, but it's too small. So that's the tympanic membrane, it's the eardrum. Inside there, we got, of course, in the ear canal, we got a whole bunch of glands. You know, you got earwax coming out and all that. The cerumen is the earwax, but that's good. It's a sticky trap for foreign bodies and repels insects. We don't mind that. Just once in a while, it's a little too much. And then the middle ear contains 3 bones. Ossicles are little bones. They're known as the malleus, the incus, and the stapes. I don't make you study them. 3 bones. 1, 2, 3. They end up at the oval window. And the oval window is right here, which is the beginning point of that snail structure. And that snail structure is known as the cochlea. And that's where we got to go next. Also, this here is the middle ear. The middle ear is closed ear to here from the outside world. So its pressure is not pressurized with the outside world. So we got to have a mechanism of being able to do that. Otherwise, that hurts a lot. You go up in the mountains or in the airplane. Does it hurt in your ear when you go up in the airplane? So you have to do this or chew gum. That's because the pressure change puts pressure in your ear, and that's not comfortable feeling. So we have a tube that called the eustachian tube that goes from the middle ear to the nose, and that equalizes the pressure out. But that's not always open. So when we force the air out, or we force the air this way, we force it up, we open it up, we make it patent. Also, this tube is more horizontal in kids. They have stuff in the nose traveling to the middle ear, giving infections in here much more frequently, and that's why that's the case. But that's two little tips on that front that I picked up along the way. When we get to the inner ear, that consists of, well, the inner ear is interesting. This is the inner ear right here. So we got this cochlear thing, this round snail thing, right here. That has to do with hearing. That's what we're going to talk about first. And then because over here we got this whole other structure, and that's balance. I'm going to talk about that in a minute. But they're both, other than shape and what they code for, they're similar in structure. So they both have, those channels, those are channels that are carved out in the bone. These things are carved out in the bone. They're not like you got a bone and then you take those out and it's in there. It's carved out in the bone. And so that carved out structure has fluid in it, and that fluid is known as the perilymph. Okay? And so we go through the cochlea, we call the vestibule, the semicircular canal are over here. We're going to talk about those secondarily. And then inside all those carved out channels with perilymph in it, we have, that's called the bony labyrinth. They call it a bony labyrinth because it's carved out of bone. But then inside of them, we got a little sac filled, a membrane filled that lays in each of these channels inside, they lays in there. And that's filled with a different fluid, and that's known as endolymph. And that's known as the membranous labyrinth. So you can sort of see it here. If you take a cross section here, you see it right here. You got, this is the bone here, and then you got, this is the filled, perilymph filled thing. And then right in here is this bag thing that goes across and holds the endolymph. And basically that makes three chambers. An upper chamber, a lower chamber, both perilymph filled, a little different fluid, and then an inner chamber, and that's the one with endolymph in it. Again, just be here for the ride. You don't need to memorize all these little things, okay? So now you got this perilymph, this endolymph, this bony labyrinth, and the bony cochlea is the bony labyrinth. It's about 3 centimeters long. It circles around 2.5 times. And then inside there is that membranous labyrinth. So let me show you. So that's again that cross section of the bone, of that cochlea. So we have this in here, this whole structure here is the carved out part of the bone. Okay, and that is essentially has perilymph in it. But in there we have that membrane structure right in here, and that cuts the perilymph in two. And then this is that endolymph filled thing. And so this is where we hear. Okay, this is where we're going to hear. The membranous labyrinth, within that bony labyrinth, makes 3 cavities. We have a cavity on top, they call it the vestibuli, don't need to memorize that. We have a cavity on the bottom, they call it the scala tympani. But we have an inside structure then too. So the scala vestibuli is the top one. Whoa. So actually, let me go back. This is where the vibrations come in from the ear that we hear. Boom, 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 boom. So it basically pushes down, right? But that would be a vibration, pushes down. So what it does then, it starts vibrating fluid in here. And that's a perilymph, the top layer of that chamber, the top layer chamber. And then somewhere along the line here, that vibration gets too big and it bangs against the top of the wall of the bone, and it pushes through the next chamber downward, which is that endolymph chamber, and goes into the bottom chamber where it then vibrates back out and just dissipates into what we call a round window. Interestingly, and see that's described right here. Oops. I know, I don't do a better job with that, huh? So that's described right here. You get the vibration coming in, the bone's vibrating, it pushes, and here we have the vibration go into that upper chamber. And then it goes up that snail. And somewhere along that snail, it bangs against the wall and it reaches over. When you cannot change that wave. The wave wants to go somewhere, that sound wave. And so if it can dissipate, it's going to dissipate. If the wall is too hard, it can't push against it, push the wall up, it's going to go down. And it can vibrate. This is a membrane, it can vibrate this membrane. Yeah, I'm not even going to talk too much about these terms because that's just confusing. And so what's cool is, what they did here is they laid that snail out and made it long and unrolled it. And so you can sort of see it because it's not so good here. But this here should be taller than the end point here. And so when sound waves come in, and they're really deep and they're really big. No, the deep ones are low, right? And they have to travel, and they're not all the same height. And at some point it reaches that top, and that's where it reaches through it. If it's, some of them, they go all the way around. The top, there has a little bit of a space where they can dissipate around it. Those are the sound waves we don't hear. It's just a little bit out of our comfort zone. So that's the organ of Corti, that whole thing, where they transmit over. And I have a picture here that you can see, but then this is blown up right here. And so now we have these sound waves that come from above down, and they start vibrating this membrane. And on that membrane, on the bottom, we have cells that have hairs that are sticking up. And when that membrane vibrates, those hairs vibrate and bend. And when those hairs bend, we get a nerve impulse sent to the brain saying like, oh, something bent there, and that's a sound. So the bending of the hairs gives you a sound. And then the question is, what sound am I hearing? Is just a matter of where along the round cochlea that vibration crosses over through the membrane where then the hairs get bent. So because we have a narrowing of the bony labyrinth towards the end, low-pitched tones stimulate hair cells closer to the apex, while higher-pitched sounds excite cells closer to the base. So the higher-pitched sounds cross over to this membrane and bend those hairs further towards the base of the cochlea, and that lower-pitched sound towards the apex. And where along the path, those nerves are that get bent, those cells are that get bent, is what kind of pitch do we hear. So it's coded that way. It's hardwired that way. The cell goes to the part in the brain, and the brain knows, oh, if the stimulus comes right there, I'm hearing that sound. Whew, that was complicated. Did you get that a little bit? So it's the bending of sound waves bending hair cells. That's basically the bottom line of hearing. And then when we get to hearing loss, what's interesting with hearing loss, we can have multiple reasons for hearing loss. We can have hearing loss because the sound waves never reach the nerve or the hair cells. Or we can have hearing loss that the hair cells don't get stimulated to transmit the nerve to the brain. So it could either be a sound wave, a mechanical, they call that problem, or a nerve problem already when the nerve gets transduced, and they call that a neural problem. And so it's really interesting in how we can test for that. We can test for that with a test called the Weber-Rhine test. So we take a tuning fork and we see, can you hear? How far out can you hear? So do you test each side? He said, I cannot hear here too well. It's not as good in here. And then what I can do is I can take a tuning fork and put it on top of the head and see if they can hear both the same or one's less and one's more. Because if the sound wave sounds is less here, when you're on the left side it's muffled, but when you put the fork on top and it's both sides the same, you know the hearing, the deficit is not because the nerves don't work, because the bones conduct sound vibration waves, and they vibrate those cells as well. And if the vibration from the skull vibrates those cells, and then we hear, we know they're not broken. But somehow the vibrations, the sound waves don't reach those cells if I don't hear so well on this side. And so they will call that a mechanical problem. I probably got some earwax stuck in here. Or maybe I got, too much AC/DC. And then all of a sudden my ossicles don't work no more right and they get stuck or something. That's, a very good reason, unfortunately. I love my music.
So, let's say you do a hearing test and the sound is too loud and it hurts.
In a test?
Yeah, the hearing test. Like,
You might want to tell them.
and you're like, I heard so bad, but it's loud, but then the other ear is normal.
I don't know. What did they say? They say anything?
No, I didn't get tested yet.
Hmm?
I said, no, I didn't get tested.
Oh, tell me what they say.
Okay.
Because I don't know. I mean, I don't know. Maybe this is your magic. Or is it overwhelming? Is it very overwhelming when you hear? Sometimes too much stimulus that goes more towards, I don't know. But ask. I would like to know what they're saying. But I would imagine it's somewhere in the brain how the stimulation is, the volume is not right, or the other side is just has a deficit, and that's not picked up. Hyper hearing. Okay, so that's the hearing. Then the equilibrium works pretty much the same way with the hair bending thing. We got two types of equilibrium. We got this equilibrium feeling. So that's the canals here that go for forward, sideways, and turning around. So it's 3 different directions. And then we got the occipital and saccule, and they're down here, more in the bottom. And they're for horizontal acceleration, deceleration. That's when you're in the car, you go real fast, or in the airplane. And vertical, that's the elevator. That's for those acceleration, decelerations. And you know those. When you go up in the elevator, it goes woo, and then it stops, and you feel like it goes, that's basically the these, in the saccule, there is a gel on these hairs, and they go up and down, and when the elevator goes up, the elevator goes faster than the gel can go. It lags behind a little bit. That's why it's like, whoa, and then it's normal. And then when it's normal, they lag behind, they're back balanced out. And then when it breaks, it's the same thing. It's just the opposite way. And the brain knows if they go one way, that's acceleration. If they go the other way, that's deceleration. Getting slower, getting faster. Same as the occipital, and that's just for forward, backwards. So that would be the airplane. So those, you don't need to know those words. But then the semicircular, well, at some point you might. But the semicircular canals are also cool because they go right around like here. See, they're really 3 canals. And what you have in there is at the bottom of those canals you have a little cupula that sticks up, and there is hairs coming up. The gel is the cupula that's on the hairs. And when we move, let's say we turn, the fluid moves around in the circle, but these stay behind a little bit because there's a lag time. And so when you turn around, it's like, oh, I'm turning around, it gets dizzy. Those are lagging behind a little bit. And when I'm turning around and I'm all cool with turning and everything is normal when I'm turning, they balanced out. The fluid is as fast now as everything else. And when I stop, then it gets all dizzy because it all goes backwards the other way. And that's when the kids fall down. That's that chair thing, and then you stop, and it's all like the whole world turns. That's phenomenal. But it's a hair bending event, and it just with that gel on, it's a lagging of the hair bending event. So I think that's really cool. Really cool. Oh, there you go. And that's just all the language around it, all the different words. But that brings us to taste. And taste and smell are both, when we have chemicals, chemicals dissolved in liquid, they get picked up by some chemical receptors. And in the tongue we have taste buds that are mostly found in taste papilla, that's just language. And they are stratified squamous epithelial. They surround the pit. So what you have here is you have these gustatory hair cells on these taste buds. And they have hairs again on top. But this time the hair don't code for movement, they code for chemicals that get dropped on it in solution. And so we got multiple different taste buds that can be tastes that can be picked up by different taste buds. We're thinking the different taste buds pick up different tastes. And the different tastes are sweet, sour, salty, bitter, and umami. That's all you pick up on the tongue. So if you got a stuffy nose and your food tastes like it does. Because you only pick up sweet, sour, salty, bitter, and umami. And umami is MSG, it's the beefy taste. It's the like, you know MSG in Chinese food. MSG? No? Monosodium glutamate? Makes it like flavorful. That's the flavorful. It's the muddy. You guys know? No? Depends where you live, I guess. Mochi is big in Asia. And so everything else that we eat food and taste with is smell. 80% of our experience of food, what we think is taste, is actually smell. And so that happens right here up in the upper nasal cavity, and we have very, very sensitive cells up there that pick up the volatile chemicals that are trapped in moisture right in here. And there is many different possibilities of odor binding to receptors, but then they reach through and they get to these different cells that combine different odors together, and it gets all complicated. And that's why we can pick up so many different types of odors. And from there, we have, once we get, you look at the brain, so it's right here on the skull. These are the holes that go, these are the cribriform plate that's right by the crista galli. And there, right here, are the olfactory bulbs that come down. And that's the cranial nerve number 1 that then reaches backwards, and that one goes not through the thalamus, that one goes right to the olfactory cortex. And then from there we go straight further on to the limbic system. And that's the smell. So again, little hair cell things that pick up chemicals. Good. All right. So with that, I think we have as a lab. Any questions?